fractions. So the first thing we want to do again is we want to critically think. So when you approach, let me fix these lights in here. That display goes down, that display goes down. Let's go down a little bit. So, okay, so pattern recognition. All right, here we go. Are you ready? What do we have on, what is in here? What's in our integral? A polynomial divided by a polynomial. In fact, I've got a binomial divided by a trinomial. Okay. We haven't talked yet what to do when you have a polynomial divided by a polynomial. Okay. So, this is why we need another technique. It's not Pythagorean theorem. We're not seeing that in there. But we're seeing functions that come up quite a bit. Can I cross out the negative 3's and write 5x over x squared minus 2x? No, why not? Because they're polynomials, and you can't just take off pieces of polynomials. So what do you do to simplify it? What would be one thing we do to simplify this if we could simplify it? Factor the denominator and see if you can cancel anything. You guys want to factor that? Of course you want to factor that. Don't you want to factor that denominator? You're like, oh my God, Tina, that's so easy. There's a lead coefficient of a 1. It's not even a cubic, is it? I just got x squared minus 2x minus 3. John, isn't it just beckoning, saying, factor me, factor me? I don't know. I just like saying factor me. Aren't you thinking that? Acacia, did you factor that out for me? What do you get? X minus 3, x plus 1. Yes, we do. So here we go. This guy, says, okay, I have a binomial over a trinomial, or a polynomial divided by a polynomial, a ratio of two polynomials, rational function. And I'm thinking, well, I can't cancel until I factor, and so I'm saying, okay, Acacia, help me out here, x minus 3, x plus 1 dx. Can I cancel anything, first of all? Okay. Does it make it any simpler yet? Not quite, because I've got products still, and then that would be integration by parts, and that would be icky. So what we're going to do is we are going to integrate fractions by going backwards. Let me explain. So we need to practice something really fast here first. Okay, let me practice something first. So we're going to get back to this. Hold this right here. Hold this thought. Just keep this on. Just keep this in your mind. But I want to go practice something over here down the bottom of my page here. Suppose I have, and I'm just going to make up some numbers right now. Suppose I have negative 4 over x plus 2, and I want to add to it 3 over x minus 7. Suppose I had two fractions, negative 4 over x plus 2 plus 3 over x minus 7. How would I do that? Find a common denominator. All right, we should go through this process. Okay, so we're going to find a common denominator. What would my common denominator be? So suppose I wanted to combine these, and Ethan says, first step is find the common denominator. And it would be what? X plus 2 times x minus 7, right? Now, what would I have to make sure I did? If I want to change the denominators, I have to do it top and bottom. Are y'all with me? So we would do it top and bottom, and then we would put them together. So on top, I would have minus 4 times x minus 7, and then I would have x plus 2 times x minus 7, and then I would have, and then I would have plus 3 times x plus 2 over x plus 2 times x minus 7. And then I would say, look, I have a what? A common denominator. And so I can do what to them? You guys are really good at this, right? You can put them together on top of a common numerator. You guys have practiced this in pre-calculus, you practiced it in foundations for calculus, you practiced it in trigonometry, you practiced this in calculus. Getting a common denominator, putting together our fractions, and then what would we do? We would do what? right? Now we would use distributive property, thank you. So now we would distribute, and on top, see if you don't get what I get. I would get, if I work this out, minus x plus 34 all over x plus 2 times x minus 7. I think that's what I get when I do that all out. But the idea is, what do you notice I have? When I add up two fractions, I get a binomial over a factored trinomial, don't I? When I add up two separate rational expressions, negative 4 over x plus 2 plus 3 over x minus 7, and I go through the entire process of putting those fractions together, notice what I get with a binomial over a factored trinomial. Isn't that where we're at in our integral? In our integral, we have a binomial over a factored trinomial. So it would make sense then, if I can't integrate something messy, to break it apart into two separate, simpler rational expressions that are added together. Because I can integrate these separately because of the addition sign. Are you with me? So that whole process, how many of you guys remember doing partial fraction decomposition at some point in your lives? Let me see a show of hands. How many of you don't even remember doing partial fraction decomposition? Okay, some people haven't. So we're going to make sure we go through this. But the idea is we are going to be starting here at this point, and we are going to rewrite it so that our integral working backwards becomes two nice, simple, rational integrals with denominators that we can work with and fractions and things that we can work with. So we're going to start with a binomial over a factored trinomial, at least in this first example, and work our way backwards to here. So that's the whole thing we want to talk about, partial fraction decomposition. So let's see. We want to break this up. So we want to take this integral and we want to break it up, and I'll just put this little note here. We're going to break it up as a sum of two simpler rational expressions. In other words, we want to rewrite our integral 5x minus 3 over x minus 3 times x plus 1 as a sum of two smaller fractions. And I'm not quite sure yet what goes on top. So let me just erase. I'm not sure what goes here. So let me just emphasize, we're not quite sure what's going to go on top. But that whole process of finding what has to go on top is the process of using partial fraction decomposition. So we want to take and decompose this fraction, okay, into smaller parts. And we want to figure out how to get those. They're not going to be the same numbers, probably, or the same expressions. So therefore, what we want to do is assign a variable to this and assign a different variable to this. So in general, we assign different variables because chances are 99% of the time they're not going to be the same. So we're going to assign to each of these fractions. Oh, undo Tina. So we want to assign to each of these rational expressions or fractions a different variable. So the whole goal will be to decompose the 5x minus 3 over x minus 3 times x plus 1 into a over x minus 3 and b over x plus 1. That means I need a thought bubble because I need to do some thinking. So I need to do some thinking to get this to make it all nice and neat and working out. So let's see. So I have 5x minus 3 over x minus 3 times x plus 1. And I want it to equal a over x minus 3 plus b over x plus 1. And I said we need a common denominator, right? So we're going to use a common denominator to put these two together. The first fraction is going to get multiplied by x plus 1. The second fraction is going to get multiplied by x minus 3. So I have, and I'm going to reiterate what I have 5x minus 3 over x minus 3, x plus 1 equals, on top, a times x plus 1 plus b times x minus 3 all over x minus 3 times x plus 1. And I'm just going to stop there. Once I get those common denominators, right, then I know I can put the numerator on top of that common denominator. And I'm just going to stop there. Does that make sense? Some of you guys might have them already have A and, what is A and B, just so I get the same thing that you guys are getting? What did you guys get for A and B, some of you? What'd you get? Any numbers? Anybody get numbers yet? Okay, so let's see. Now, at this point, there's a lot of ways to solve this. I want to stop and use my brain. If I have the same denominator, what does that tell me about my numerators? Robert? They have to equal each other, right? I have identical denominators. That means my numerators have to also match. So that means I can continue along this thinking path and say that means 5x minus 3 has to be a times x plus 1 plus b times x minus 3. Since my denominators are equal, that means my numerators have to be equated. Or in other words, I could just take this equation and multiply both sides by the common denominator, x minus 3, x plus 1, and it would cancel both sides. So my denominators are equal now, so that means my numerators are equal. Now, at this point, we could do one of two things. We can either distribute and create systems of equations. And I love to do it that way. But students like shorter ways. And so let's do some more thinking and observe. This is an equation. That means whatever I plug into x on the left, I have to plug into x on the right to keep it all balanced. Wouldn't it be nice if maybe I decided to plug x to be negative 1? If I plugged x to be negative 1, what would that give me right here? A 0. 0 times a makes a disappear, and that will tell me what b is because I'm just putting negative 1 wherever x is. Do you see what I'm saying? Our goal is to figure out what a and b is. And so it kind of would be nice if I created a 0 right here. That gets rid of my a variable and solves for b. So that's what I'm going to do. Got it? Here we go, Tim. So we're going to let x equal negative 1. When I do that, it makes this here will go to 0. So let's see. So if I let x equal negative 1, it's an equation. I have to plug that value, negative 1, in everywhere we see an x in that equation. Pretty? Did you get a b then, huh? So then this goes to 0. 0 times a is just 0. It drops out. Okay, so what do I have as my equation then? My equation is going to be negative 5 minus 3, which is negative 8, equals, that term dropped out, b times negative 1 minus 3 is going to be what? Negative 4b? Are y'all with me? We divide both sides by negative 4. Can you tell me what b is going to be? b has to be 2. So I now know what b is. b has to be 2. Nice! What's another number that might work nicely for us? Let's let x equal 3. I do want to say this method of zeroing out doesn't always work because sometimes we'll get factors like x squared plus 7 or something like that, in which case you can't zero it out. Are you with me? In which case then you probably want to set up systems of equations. But for now, this whole trick of zeroing out is a really wonderful way to solve this. So you're going to let x equals 3. And everywhere you see an x, you're replacing 3. It is an equation. To keep it balanced, whatever goes on the left side must also go on the right side, right? That's the whole definition of an equation. This is going to, again, give me a 0 on the b coefficient. And so that's going to make, what is that? 15 minus 3. Are you guys getting 12 equals 4a this time? And we're dividing both sides by 4. And so that tells me that a is just 3. And so that's going to tell me that if I want to simplify this binomial over a trinomial, and I'm going to erase this other stuff, I can rewrite it as a, which is 3 over x minus 3, plus b, which is 2 over x plus 1. And why is that nice? That's nice because I now have 2, and you check it. That's 3x plus 2x is 5x. Plus 3 minus 6 is minus 3. It all works. It all works. Always good to check it. Always works nice. But what's nice for us now is instead of starting with this complex binomial over trinomial, I now have 2 simple rational expressions to integrate. They're added up, so by the properties of integration, I can separate those 2 rational expressions and integrate them separately. How do you think you want to integrate those? What are you thinking? Zach, what are you thinking? You're smiling. What are you thinking? U sub, absolutely. You can do a very simple U sub. All right. What would you let u be on the left? You would let u be x plus 3. du is simply dx because it's just linear with the coefficient of 1. And so what does that integral become? That just becomes 3 du over u, which is just... It is x minus 3. Oh, thank you, Acacia. You're so good to catch that so fast. X minus 3. Good, good, good. Thank you, thank you. All right, so now I go back. 3 over u du. 3 ln of u, absolute value. And then we substitute, back substitute, and that's going to give me 3 times the natural log of the absolute value of x minus 3. Look how easy that was. Was that like a piece of cake? And the other one, and I'll walk through the steps, okay? As you get better at this, and as you do more and more of these, sometimes students will skip the u sub and do it in their head. So rather than writing it out, they'll just do the u substitution in their head. But for now, I want to write this out for us. So we do another u sub, and that's going to give us 2 du over u again. That's going to be equal to 2 times the natural log of the absolute value of u, but this guy's green. And so when I go back to substitute, that's going to give me 2 times the natural log of x plus 1 plus c. Ta-da! Once you break up that polynomial divided by polynomial into 2 simple rational expressions, your integrals become simpler to work with. And often you can simply use a u sub to finish it off. Often. Not always. Not always. Who's got questions? I know. I got to say, that is so cool. That is so cool. Who's got questions? A lot of students find this to be their favorite method. Some people really enjoy partial fractions.
When you separate the integrals,
yep.
I brought the x minus 3 up.
I wrote it to the -1 power. You can do it that way. And then you did a u sub with that, and then you recognize that as a natural log?
Yeah.
Yes, you can do it that way, 1,000%. Other questions? Other questions? You guys ready to try one? Okay, here we go. Practice problem B. Evaluate the indefinite integral. Notice I even factored it for you. You're welcome. You're welcome. Oh, you want practice factoring? Is that what it is? I mean, I can give you practice factoring. Trust me. We have so much practice we can do, but I'll tell you what. We're going to focus because we are just working right now on practicing adding fractions and getting A's and B's and doing all this. We have enough stuff up there to worry about. So x plus 16, antiderivative of x plus 16 over 2x minus 1 times x plus 5. I do know that your A and B turns out to be integer coefficients. On your web work, they will often be fractional coefficients. We will practice fractional coefficients for A's and B's as well in this class. But for now, your A's and B's will turn out to be nice integer values. Alrighty. So off you go. I'm going to wander, and then you can ask me questions. Guys getting nice integer values for those A's and B's? I get B as -1. Is that what you guys are getting? Well, the value on top of x plus 5, if that's how you broke it up. Oh, this x equals 1/2 is a little trickier. So 1/2 plus 16 equals A times 1/2 plus 5 plus B times 0. 2 times 1/2 minus 1. So that's 0. So I get 1/2 plus 32 halves, and then 1/2 plus 10 halves. So I'm getting 33 halves equals 11 halves A. Flip and multiply by the reciprocal, 2 over 11. That's giving me cross 3. 3 is A. You guys got 3 being A. So let's see. We've got the integral of 3 over 2x minus 1 plus the integral of of -1 over x plus 5. Does this match what you guys did so far? Quick U sub. Quick U sub here on the front end. U is 2x minus 1. Du is 2 dx. 1/2 du is dx. Don't lose that half that's coming from that 2 in our U sub. So when you're making your U substitution for that first part, you should have 1/2 times 3, or 3 halves times 1 over u du, which is just going to give you 3 halves times the natural log of the absolute value of u for the first part. So that first part is going to be 3 halves times the natural log of 2x minus 1. The second one, Again, you're going to get so good, you're going to just do these u subs in your head, but you notice du is just dx. This is just minus du over u, which is just minus the natural log of the absolute value of u on the second one. So you guys are getting minus the natural log of x plus 5 plus c. Who has questions? Who has questions? Who's got questions? Questions, 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 questions. Questions. Anyway, what do you think? Not bad? Partial fraction decomposition, okay? When do we use it? When we have a polynomial over polynomial. We started with some simple ones. I don't think I want to start with any more examples right now, okay? But what I am going to talk about next time is, so what happens when you get repeated factors? Like, let's say on the bottom it's 2x minus 1 and 2x minus 1. Or 2x minus 1 squared times x plus 5. Or what if you have a cubic down there on the bottom? How do you work with that? Or what if the degree on top is bigger than the degree on the bottom in your polynomial? You got to do some simplification before you use partial fractions. So we're going to look at all kinds of special situations and special cases next time, all right? But